So, I guess we're almost ready to start. And firstly, I want to ask Satiris, in what language should I speak? In Russian or English? All right. Okay, so, wow, I'm really happy to see all of you here in Yaroslavl, in the head office of Tensor company, which now is an organizer of your great conference. The name is too difficult and complicated for me, so just read it, please. And all of you, of course, know why you are here. And at first, I kindly ask you to keep social distance. You know, there is a great conference hall. There are a lot of empty seats here. So, if it is possible for you, please feel it and keep social distance, because you know it's not our it's a rule and you should keep it, especially students over there. Рассаживаемся, друзья, рассаживаемся. Места много. So just a few words about our company. We're really very glad to be an organizer of such a great conference, because Tensor company and the Middle States Universe are partners and friends in engineering and scientific developments, and it's really cool, I think. My name is Anna, and I'm a head of educational department of Tensor company. The company is fond of software developing for business automatization, and if you want, later I can explain you what does it mean. And now just a few words about your schedule. Please be careful. All of you have a paper in your bags, in your blue bags. Please keep it now and read it carefully together with me. So usually your working day will start at 9 a.m. and please everybody be here on this time for you to start it immediately. And then every day you will have coffee break in 11 a.m. And the coffee break every day will be on the 7th floor. So it is a small stairs over there behind the conference hall. Please keep it in mind. And also every day in one and the same time you will have lunch. You will have 1 hour for lunch from 1 a.m. to 1 p.m. to 2 p.m. And it will be on the 1st floor in our restaurant called Mili. So please use the elevator to go on the 1st floor. And then, if you don't know how to go to the restaurant, just ask somewhere or our employees. They will help you. Also, you can use stairs. If you feel yourself strong enough, you can use stairs or behind the conference hall. And also, every day in 4:30 p.m., you will have another coffee break on the 7th floor. And at 6 p.m. it's stop working, and we will ask everybody to go and have some rest. And about some rests, today at 6:30 you will have welcome party, and we will be glad to see all of you at this time on the second floor. Ask Satiris if you don't know how to go. He will be with you. Tomorrow evening, we will have another small holiday, how to say it, with special dinner in our restaurant Mili. And also on the third day, you will have excursion, so it will be a short working day. The most important information about our Wi-Fi, if you don't know the password, it's really simple. Please access if you want. And that's all. And now I'm glad to introduce you rector of the Demidov State University, Alexander Ilyich Rusakov. Please take your words. Александр Ильич, дайте нам пару минут, мы настроим звук. Вас очень плохо слышно. Вас просто плохо слышно. Сейчас мы сделаем немножко погромче, чтобы все было в порядке. Ну что ж, попробуем еще раз. Александр Ильич.
Теперь слышно хорошо.
Да, в самом деле слышно гораздо лучше.
Let me again introduce you, Alexander Ilyich Rusakov.
So thank you so much for the introduction, and I would like to say that it's a great honor for me to say words of welcome to the second International Conference on Integrable Systems and Nonlinear Dynamics that we are very pleased to host in Yaroslavl, together with our partners and friends at Tensor company and Yaroslavl State University, named after Pavel Demidov. So the opening ceremony is still with us, and I'm very glad to welcome you, those who came in person to our city, to the great building of Tensor company, and to take part in the great conference. So a great list of the participants includes a very fundamental names, the names that are a glory of the international mass. So it's an honor for us to welcome academicians Kozlov, academician Treshov, academician Burstaber, and also a special welcome to Anastasios Buntis, who will probably be one of our partners in the nearest future. So during the pandemic, it's a great courage for those to come in person to Yaroslavl and to take part in the conference. So words of welcome to everybody and the wishes of success. I wish you all to come to Yaroslavl again after this pandemic will be over and we can really take the great conference again. So we are very welcome. We give thanks to our partners in Tensor company and all those who were the real driving force of the organizing committee of the conference. Я уже третий раз все повторяю, поэтому, наверное, лучше без меня.
Все было хорошо слышно. Спасибо.
Да, все было слышно. Да.
Ну что ж, Satiris. Just a few words about how to make your speeches. So it will be great if you will come here on this small stage and use the microphone, the clicker, if it is convenient for you. Just come here.
Okay, it's my pleasure to introduce Professor Vladimir Sokolov from Landau Institute for Theoretical Physics and University of São Paulo in Brazil. He will speak about non-abelian evolution systems with conservation laws and symmetries. Welcome.
Thank you. So thank you very much for a new opportunity to visit your nice town. About my talk, I can say about 20 years ago, I attended to a lecture by Atiyah, and the title of the lecture was Mathematics in the Next Century. And his claim was one of the main problems is generalization of different abelian objects and constructions to the non-abelian case. I am follow just this program, and I would like to speak about differential equations where a known function is not a scalar, usual scalar function, but a matrix. So in our differential equations, we will have a matrix depending on t or x, or it depends on the... in the previous conference, if I am not wrong, I discussed differential equations, ordinary differential equations with matrix variables. Today, I am going to speak about partial differential equations. This is references, and this is the main paper, very recent. I will follow these results. But before, I want to stress, for me, this is just a miracle. Almost all integrable, I am not going to discuss what does it mean, integrability, but I would like to claim that almost all integrable, usual integrable models has some matrix integrable generalization. For example, this is one of the most important integrable model when u is a scalar, usual function depending on t and x. This is partial derivative with respect to t, and this is derivative with respect to x. But I claim that this equation, where u now is a matrix of arbitrary dimension, is integrable. Now, this is important, I mean, the fact that the coefficients here are equal. Now, u and ux do not commute, and this is important. But just in the case where these coefficients, 3 is not important, but important that this coefficient equals to this coefficient. This is an integrable model for any size of matrices. Now, the next example. If u is a function, we have the well-known modified KdV equation, integrable also. In the scalar case, this is ut equals uxxx plus 6 u square ux. But
Can I interrupt for 1 second, because not everyone can see your screen, so sorry about that. Я это сделаю, да. Вот. No, sorry about that. No, now you can continue.
okay, thank you. The next example, you see that these two matrix equations, they coincide if the side of matrices is 1. But if this is really non-commutative situation, this is not 0, and these two equations are different, really different matrix generalization, both are integrable. Two different generalization of just one scalar equation modified KdV equation. Now, several examples more, simply to stress that we have some rational equations matrix also could be integrable. For example, this is a matrix generalization of so-called Schwarz-Cauchy equation. And again, this is integrable for arbitrary size of matrix U. Okay, let me skip some examples. Maybe we can look to this example. This is also integrable. Also U, V, and W are matrices. But here we see also transposition of matrices. It's some new effect. Sometimes integrable generalization contain transposition. But the main question is, suppose we have a scalar integrable model, and we want to find all possible integrable matrix generalization. How to do that? It turns out that this is very simple, in some sense, procedure. And it was understood only a couple of years ago. And I want to discuss this and to show how it works. But before, what I should say before, first remark is, in all such systems, matrix system, actually we don't want to work with entrances of this matrix. It's we want to work only with non-commutative polynomials. I will use non-commutative polynomials with respect to u, ux, uxx, and so on. This means that actually this is not matrices. They are elements of associative algebra. And it's enough for us. It would be free associative algebra. Free means that we have no algebraic relations between u and derivatives. They are symbols, they are non-commutative symbols, and I want to play with these symbols. It's enough to construct all generalization. The next point today, and when I'm speaking about generalization, this construction of non-abelian, non-commutative generalization, I will work with homogeneous polynomial differential equations. Homogeneous means that our equations, and most of them, for example, KdV, modified KdV, all these equations, they admit a scaling group. We can use the scaling with respect to parameter t, and for some mu, nu1, nu(n), our system is invariant with respect to this scaling. For example, if we look to this system, it's very easy to verify that this is invariant with respect to any scaling with mu equals to 2. And even in nu1 and nu2, we can see arbitrary parameters. So it's a very rich scaling group for nonlinear Schrödinger equation. It's known, if you want to work with nonlinear Schrödinger equation, it's useful to rewrite this in the system form. Roughly speaking, u and v are real and imaginary part of a complex function in the nonlinear Schrödinger equation. No, of course, you can find these parameters, these degrees of homogeneity for any previous examples. But now what I want to generalize. Let's consider the following integrable systems, quasi-linear in the first derivative. For example, this scalar, in the scalar case, this system belongs to this class. And it was a serious classification job. All systems, for example, not only this, all systems with arbitrary right-hand side here, all integrable system of this kind was classified in the old paper by Mikhailov, Shabat, and Yemilov. And I want to consider only this subclass of integrable models. Why? It turns out that all integrable models of this class are polynomial. Polynomial with respect to u and v. All these coefficients are polynomials. And I want to generalize, of course, polynomial integrable models. And if we look at the paper, carefully look, we will see that this is the complete list of integrable homogeneous models from our class. This our nonlinear. This is commutative. This is just systems from the Mikhailov, Shabat, Yemilov paper. And this is a complete list. What's interesting here that we have some parameters. We can kill one parameter by scaling, but there is some assertional parameter here. And the second important point is that there are two classes, two subclasses in this case. And they are so-called nonlinear Schrödinger equation type and Boussinesq type equation. What is the difference? This is a list of nonlinear type integrable systems, and this is so-called Boussinesq integrable systems. And we want, this is the main aim of our paper with Seva Adler, to generalize, to find all generalization of all these systems to the non-commutative, non-abelian case, matrix if you want. And what is the main idea, how we want to proceed? The main idea in general is the following. Integrable model, scalar integrable model, it has many algebraic objects related to them. Lax pair is not well-defined object, but such object like symmetries, high symmetries, or conservation laws, local conservation laws, they are related to the equation. You can calculate them for given equation. So we have a lot of additional objects. And I want to find such generalization that for the non-abelian equation, we have the same set of integrable objects. We have non-abelian symmetries, we have non-abelian conservation laws, and our requirement is if the size of matrices is 1, or in other words, we goes from non-commutative to commutative case, all this stuff, all these symmetries non-commutative, all these conservation laws, all of them should map to the corresponding object for abelian integrable model. It's very natural, and it turns out it's enough to find all non-commutative generalizations. So now I want to show how does it work. So if you want, we can look to the formal requirements, but they're evident. First of all, we want that our non-commutative generalization have the same scaling group. They are polynomial, non-commutative polynomial with the same mu, nu1 and nu2. Second, of course, if we go from non-commutative variables to commutative, we have the initial equation we want to generalize. And the third, all in our paper here, we are working with conservation laws. All non-commutative conservation laws should go to the corresponding commutative one. Before going to explicit formula, we should discuss what is local conservation law in the case of non-commutative or matrix systems. So actually, on the informal level, we are dealing with functionals of this type. We have a polynomial of non-commutative variables, they are matrices, just here in this formula, and we can trace, and if we assume that U, V are solutions of our systems and solutions of solitonic type, this guy in general does not depend on X we integrate with respect to, but it could depend on T, because U are a function of T and X. But our requirement is for any solution of our equation, this integral does not depend on T. It's a conservation quantity. First integral, but first integral in this case not a function, but a functional. And in the matrix case, additionally, we can have trace. But we want to generalize, to formalize this. First, we don't want to work with matrices. Second, we don't want to work with the integrals. We want to work only with this polynomial, which depends on non-commutative variables. How to do that? First, I want to stress that if we add some total x derivative to here, the value of the integral is the same, because we find the integral of the first x derivative. This is, we know this function, we should substitute plus infinity and minus infinity to this function, and they are zeros because we assume that U and V are solitonic type functions. So first we could add to rho any total derivative in X, and second we could add any commutator of our variables, because trace of commutator is zero. So the function rho is the density, is defined up to total derivative and up to commutators. So we are working with this vector space. This is a set of all commutators, vector space, not algebra commutator, but vector space. It's a linear combination of some commutators and total derivatives. And we want that our t derivative is zero up to this vector space. We are working with the quotient space with respect to this vector space. So this is the definition of conserved densities here, and we are working with just this. We need some non-commutative polynomials such that if we differentiate them with respect to t, with t means t derivative with respect to our given differential equation. This is again a polynomial, and it should belong to this. We can see an example just in a minute. Here I want to stress that we have several, very often we have several non-commutative generalizations, but some of them are trivially related. For example, they could be related to the following evolution. We consider them equivalent, because if we have integrable models with respect to U and V, we have integrable models with respect to conjugated variables. It's the first in the definition of equivalency. And second, sometimes there are some scaling or trivial transformation which relate our different non-commutative generalization. So we want to describe all non-equivalent, non-commutative generalization. Okay, it's an answer. How many generalizations we have? This is the number of generalizations for each of equations from our previous lift. For some, no generalization, and for one of them is 8 different generalizations, but the number of non-equivalent, if I'm not wrong, is 3. But at any rate, and what's interesting here is, if you remember, in the scalar case, we had integrable models with 2 parameters, alpha and beta. It turns out that only for special values of alpha and beta, we have non-commutative generalization. And by miracle, these 3 models are well known in the literature about integrable systems. I have no any explanation of this fact, why these values of parameters are the most important in different sense. Okay, now I want to discuss the system, I call it B2. Let's go back, not back, let's go back. B2. This is just this system. For the first glance, very simple. And I want to find all integrable generalization of this system in my talk. Okay. First, how our generalization could looks like. Just this. If you want to think which non-commutative polynomials you can place here, you see, and it should be homogeneous with the same homogeneous weights, you see that only 2 possible unknown parameters you can additionally put to the right-hand side. Here, no chances to put any non-commutative terms, but here we can add commutator. In the scalar case, it disappears. And also we can find the commutator between V and Vx, here and here. So the problem is how to choose alpha and beta such that this equation is integrable model. Only 2 parameters, scalar parameters, are unknown here. Now we are working with this system. First of all, in the scalar case, these functions are conserved density. You can calculate it by computer or by hand. It's a trivial linear problem to calculate the conserved density for the given system. And I want to generalize all these conserved densities in the non-commutative case such that they coincide with this in commutative limit, and it should have the generalized so first we start from the trivial density. This is the only possibility to generalize, simply think that V is now non-commutative V. But we find that the derivative of this guy is just right-hand side, but it's a total derivative, so no information about our parameters alpha and beta. The same story with U and UV. Now they are non-commutative. We look to this, and we see no information about alpha and beta still. The next, I demonstrate here that for this density for we have no any information at all, because the right-hand side is the total derivative plus 2 commutators. So it's a trivial function, no information about equation. So in the next case, we go to the next conservation density, conserved density. It should be of this form, non-commutative polynomial. No more possible terms here to generalize our commutative density. Now we substitute and we calculate the total derivative. We find a following expression. We see total derivative, it's trivial, 2 expression with commutators. It's also trivial, but this is non-trivial term. This is not total derivative, and this is not a commutator. You can verify this very quickly. So you find the first condition, alpha equals to beta plus 1. And now we go, but it's still linear relation between alpha and beta. How we can find several generalization? You can see it to the next step. So we take the next scalar conserved density and see that the most general generalization of the conserved density is just this. And we see in the first time we have an arbitrary parameter in the conserved density. We should write here the most general. And in the most general, we have these guys. In the scalar case, they disappear, but in the non-commutative case, we have these 2. Now we substitute again, find the t derivative and look what does it mean that this is conserved density. We kill some total derivative, we kill some commutator, and it turns out that we have, in this case, only 2 algebraic relations between this unknown parameter in the conserved density and with the remaining parameter on the right-hand side. We have just this system. We solve this and we find all possible betas. You see that we have 2 different values of beta. That's why we have 2 different non-commutative generalizations. In this case, they are equivalent. There is some transformation between systems, non-commutative systems with these different values. But in different cases, it's not so. And now, okay, we do all this computation for all systems from our list. And we find what? We find several set of non-commutative systems. They are candidates for integrability. But to finish my investigation, I should really prove that they are integrable. And in this case, we switch to the so-called lax pairs, or if you want, zero curvature representation. For all our systems, non-commutative, we found the lax pairs depending on spectral parameters. So this is a proof of integrability for all our new non-commutative models. I can show how it looks in the next example, so-called S4 model. It has 2 different non-abelian, non-equivalent, non-abelian generalization. You can verify that if U and V commute, they are coincide and becomes just S4 integrable model. But they looks a bit different, some commutators. For example, this is 0 in the scalar case, of course. This is not 0 in non-commutative. And in the last slide, you see how looks like zero curvature representation for both. This is the first. You see we have the spectral parameter I promised you. I is a unity, matrix unity. And this is U and V. And in the second case, it's a little bit more complicated. U has a similar form, and V can be written in terms of U square for shortness. And you can verify that the main relation of the theory of integrable models, this is just equivalent to our nonlinear non-abelian equation. So we can use this to apply the standard procedures to find the solitonic type solutions. And for all other tricks for integrable models, all of them are related to this representation. So that is the description of our paper with Sevadler. And I want to say, this is general approach. I can do the same for any integrable scalar model. I need only two facts. They are polynomial, homogeneous, and I can find all integrable generalization by in the same way. Now the question is just applications. If you show me really integrable scalar models, and if you can explain why non-commutative generalization are especially important in the applications, I am ready to do the same tricks. But the general theory of non-commutative integrable models is not so good developed. For example, the problems with transformations. The general claim is not so many integrable models. There are a lot of different transformations between them. And if you want to be an expert in integrable models, you should first understand which transformations could be applied to relate different integrable models. If you know, they are not different more. Okay, so probably this is all what I can say about this. Maybe 1 point more. 1 point more. As claimed Sevadler and me, we are going to work on this direction. In the scalar case, there is a standard observation how to find the ordinary differential equations of Pendlevet type from partial differential equations. You look for, I don't know, for example, for semi-similar solutions which invariance, for example, with respect to our scaling group. And for this guy, you will have ordinary differential equations of Pendlevet type. And it's very natural to, of course, in this case, it will be an equation of 4th degree, but usually it's possible to reduce the order twice to get a usual Pendlevet, one of usual Pendlevet equations. And it's very natural to use that some similar procedure could be applied for non-abelian, for matrix integrable models. As a result, we will have some matrix, integrable matrix Pendlevet equations. What I am going to check The problem is how to reduce the order of the systems in the non-commutative case and so on. But we are sure that it will work. So it's a program for the next paper about non-commutative systems of this type. So now it's a
Well, we have time for questions.
Do you have any background transformations for your non-commutative systems?
Yes, sometimes yes, but I cannot say that I can generalize all background transformations for scalar case. One of the reasons, you know, even your equations are polynomial, background transformation are not. So we should write them in the polynomial case. Probably this means that this is still not some formula, but some ideal in the non-commutative algebra. It's a point for special investigation. You're completely right with this equation.
You have those interesting Lex pairs, which are matrix and polynomial. Do you know any background transformations arising from those particular Lex pairs?
You mean Darboux transformations? You are right.
Okay,
This is a reasonable, but to do that first, I would suggest to bring this U and V to more symmetric algebraic form. You know, if you look to the formula, it's a little bit not symmetric. Lambda is not good here. You should make some transformations, linear transformations with these matrices to prepare to the Darboux. But I think that Darboux transformation works, and you will have non-polynomial formulas like logarithmic derivatives, you know,
Okay.
in the Darboux and in the backgrounds.
And then, as you understand, if you get Darboux, they will probably be, you will probably be able to get integrable discrete matrix equations.
Yes, you're right. But in this case, they also will not be polynomial in general. There are some polynomial discrete systems. You can find them in the paper by Seva Adler in the archive yesterday or today. So it's a very recent research, and this is an intensive, a lot of problems. In non-commutative theory of differential equations, there are a lot of open problems. Interesting, really interesting.
Okay, thank you very much.
Any other questions?
Oh, Володя. Володя, do you hear me?
Yes?
Hello?
Yes, but I cannot see you.
Yes. No, you cannot see me. I'm far away. Please, what about 2 + 1 dimensions?
No information.
Do you have some?
No information. I would say that first papers about non-commutative integrable models, probably Marchenko. And in his book, you can find non-commutative KP equation. And I think there is some information about it. But again, this is not so developed as in the scalar case. You are right also, it's a reasonable unsolved fresh program about 1 + 2 non-commutative. Here it's a unique situation. You can you can ask any reasonable question, and you will have a reasonable problem for research.
Volodya, I have
Nice. Okay, thank you.
I have 2 questions. The first is the philosophical one. Is the non-abelian generalization of integrable system is related with somehow related to the quantization problem?
Yes, it's a very good question, and a partial answer, I hope you will see from Sasha Mikhailov's talk today. His philosophy is, first you should find this integrable model to the free associative algebras. And second step is you want to quantize not Poisson brackets, you want to quantize the integrable model. You take it to a free algebra and look which commutative relations between fields you can additionally assume such that it's compatible with the integrable model. And his computation showed it works very well.
Thank you. And the second question, you said that you obtained the non-abelian Pindley equation. Does it have some isomonodromic interpretation?
If we take the Pindley equation by this trick, you will have the asymonodromic Lax pair, certainly. And there is one example in the paper by Adler. I mentioned it should appear today or a couple of days ago in the archive. You can see the asymonodromic Lax pair with dd lambda for one of the integrable models.
But the points now are somehow more difficult objects, or just the points?
Unfortunately, I am not ready to answer.
Okay.
This is again good question.
Thank you.
Okay, let us thank the speaker again.
So thank you very much.
There's tea and coffee upstairs at level 7, and we rejoin at 11:30. Welcome to the next session of the conference. It's my pleasure to introduce Sergei Sokolov from the Moscow Institute for Physics and Technology and Stiklov Institute for Mathematics of the Russian Academy of Sciences. Sergei will talk about dynamics of a circular cylinder and two-point vortices in a perfect fluid. Welcome.
Hello. 1, 2, 3. Thank you to organizers to have a talk on this great conference. And I present you, in contrary to the previous talk, when we can see the infinite dimensional integrable system, now we starting to observe the dynamics of circular cylinder with two-point vortices in a perfect fluid. This is the, in some sense, new case of integrability in the finite dimensional integrable systems. And in this case, we can observe some procedure to reduce to integrability in the by quadrature in the case of the 1 degree of freedom, reduced to 1 degree of freedom. Now we can start.
But I look on the paper.
First of all, we have a small recall about the point vortices interacting with the rigid bodies. We can see some highlights, historical highlights of the observation of these integrable systems. First of all, the Helmholtz-Kelvin works in which the general equation and conservation law was formulated for the simple singularity and the hydrodynamical type equations. We can see one point Z0, where our potential in this vector fields has a singular point, and this is the simple object in the 2D hydrodynamics, which has a role as the material point at the classical mechanical, like a classical mechanical. We can see at this slide three the simplest motions of these objects. First of all, this picture illustrates the single point vortex, which stay in rest at the unbounded perfect fluid. If we have two-point vortices, if they have gamma and minus gamma intensities, this is the case of so-called vortex pair. In this case, in unbounded liquid, the vortex pair moves through our liquid with a constant velocity. And if we have two vortices with the same intensities, they rotate at the same distance around 1 point. As the first step, we have a general equation in the Hamiltonian form, was obtained by Kirchhoff and Raus. And after that, Lin in the 20th centuries explained that if we have a rigid body with some boundary, this is the same Hamiltonian equations, the same form with the classical simple Kirchhoff type Poisson bracket with the Hamiltonian function, this one. We have a set of singular points as a point vortices, and this is the Hamiltonian equations of this. After that, the observations and investigation of these systems shift to the vortices on the some surfaces. This is the classical investigators. Some of these you well known: Stefanella Boata, Jair Kohler, Dritschel, and the classical one, Gromyko, Tsarmela, Bogomolov, which applied some results from dynamics of the point vortices on the plane to the vortices on the surfaces. It is very important for aerodynamics of the atmosphere, aircraft development, and so on. The classical results for the 2D hydrodynamics is the investigations of motion and stability of point vortices exterior within a circular domain. You know the Greenhill problem and von Karman investigations, the solution of Havelock, and to the modern point of view, Leonid Kurakin. In this state, we can observe some equilibrium. For instance, Föppel's equilibrium, when the circle cylinder moved through the unbounded liquid and has a vortex pair on the line collinear to velocity of this cylinder, and at this time with the some certain distance between the center of cylinder and the center of vortex pair, we have a unstable equilibrium. And for us, very important, the next step in these investigations, when the in contrary of Greenhill and Havelock problems, when we have an equilibrium around collinear configurations of vortices around the unmoved circular cylinder. At the next step, the last decade of the 20th centuries, we have and the first decade of the 21st century, we have a set of works, papers by Jair Kohler, Sergei Ramadanov, Bonavar Shashikant, Alexei Borisov, Ivan Mamayev, and Sergei Sokolov, which devoted to investigate the interact dynamically rigid body inside the liquid with the vortices structure. And we now starting some mathematical introduction on this theme. First of all, let us consider the forces on a cylinder. Now, starting with this time, we restrict our general observation for as such a case. We introduce the circular cylinder, rectilinear, and we now explore how we can extract the governing equation of this system in the presence of the point vortices. The forces which acted on the cylinder, rigid cylinder, in a perfect fluid, we now know three simple forces. First, the force due to added mass effect. If our cylinder moved to the right on the picture with velocity v, big V, the same velocity v is the velocity of the liquid outside our cylinder. And on our cylinder, we have extract for equations of classical hydrodynamics that all effects of our perfect liquid outside our cylinder in this case can be represented as the one force. This is the force that's proportional to V dot. After that, if we have a circulation flow around our cylinder, we also have a Joukowski's lifting force. At the picture we have a good represent of the direction of this velocity of our motion of our cylinder and the lifting force of Joukowski type. And it's surprised if we have the simple liquid flow outside our cylinder. We have one point vortices outside our cylinder at the position by RG. We now have an inverse image of our point vortice inside our rigid cylinder. This is only the mathematical object to conserve the boundary conditions on our cylinder. These two vortices, these two vortices, one vortex is the real and his image, coupled of these point vortices acted on our cylinder with the force proportional to the difference between velocity of our point vortices. This is the velocity of our point vortex, Rg. This is V tilde G is the velocity of his inverse image. And if we calculate differences between these velocities, the Ramadonov's work has a modern result that is the F acted on our cylinder is the proportional to these differences. Lambda G, this is the value proportional to circulation or intensity of our point vortices. We can be see below. If now we can observe the differential equation governing of our motion, we can see the system of 4 degrees of freedom. Recall that we can see one rigid circular cylinder and two vortices. We can see the velocity of center of mass our cylinder V, and this is the two equations, and the 4 equations describe our point vortices gamma 1, gamma 2, and the equation of motion in the Newton's type for our cylinder. The A is the mass plus added mass of our cylinder, and the lambda is now we can recall recall this value. Lambda is the gamma over 2 pi is the simply connected with the intensity of vortex value. And phi of R is the so-called hydrodynamical potential of velocity, which contains at this one terms at the second and first equations for velocity of our vortices, and the terms at the right-hand side of the Newton's law, we can see one terms due to circulations around our cylinder, and two terms which describe the interaction with the force, this one, with the vortex pair of our cylinder. Now we have very huge, if we substitute this phi into the gradient on the right hand side, we have a huge, very big right hand side for our differential equation. What can we do with this? Now we first of all represented the Hamiltonian form, this equation of motions, because it's not so trivial. We have a Hamiltonian function at this form. We can see that Hamiltonian function has a kinetic terms and potential terms, but not so usual for analytical mechanics logarithmic form of this potential form. And if we have Hamiltonian function at this form and introduce the Poisson brackets with the non-zero components the same form, we have previous equations of motions, this one, at the Hamiltonian form, the classical Hamiltonian form.
Is it possible to reduce these Poisson brackets to a polynomial form?
No.
It's impossible to case them?
Yes.
Do you know your name?
Yes.
Are you sure?
I'm sure. The Poisson brackets satisfy the Jacobi identity, excuse me. And this is non-degenerate Poisson brackets. This is give us some field of our observation. Besides of Hamiltonian function, governing equations from the previous slide allow two additional integrals due to the translational symmetry, some kind of conservation of linear momenta. And we have a rotational symmetry, and this is some kind of kinetic momenta, which also conservate. The Lie Poisson bracket of Q, P, and Y and I read this form, but is a non-zero in the general case, and this is means that in the general case our system rigid cylinder and 2-point vortices not integrable. But now we restrict our observation to the next conditions. First of all, we exclude circulations flow outside our cylinder. It means that lambda equal to 0. And after that, we can introduce our system on the common level of zero constant of integral of motion P and Q. And this system has a complete completed set of first integral, and this does mean that on this common level, our system, cylinder and two vortices, is Liouville integrable. And now we represent some common procedure to reduce this system in the explicit form, and we can see the explicit integration of this system in this case. And we have some illustration of motions in this case, and some type of bifurcation diagrams for the certain relations between intensities of our point vortices. Now we can start our procedure of reduced to 1 degree of freedom our system. First of all, using the momenta, I recall if the constants of these integrals equals to 0, we get rid of the cylinder velocities V1 and V2, and obtain 4 ODEs and 2 conservations law, Hamiltonian function and angular momenta. Unfortunately, this slide contains only the first differential equations of 4. You can try to direct calculate to be sure that this is a very big, huge differential equation. Some kind of for these equations, we have a system, and substitution by V1, V2 to the Hamiltonian function, we have a Hamiltonian function depends only our position coordinates, besides our velocities of our cylinder. And another one integral is the kinetic momenta of our system, and what we can do with this huge system. It should be noted the equation has a classical bracket, Kirchhoff's type equations, and this is a common procedure to reduce the system. This is the to reduce the system's order. Take the integrals of the symmetry fields as a new variables, pi1, pi4, p1, p4. This is the very simple geometric sense of these variables, because this is the distance to original point for our vortices, and this is the scalar and vector product of our R1, R2. They non-zero brackets are this one, but they are degenerate, unfortunately. They have 2 central function, and we now introduced some connection between absolute and relative motions of our vortices. The alpha is the angle between our R2 and R1, and if we integrate these differential equations in the separated variables, we can define, of course, pi1, pi4 from the from differential equations extracts from the Hamiltonian function with these Poisson brackets. We have possibility backward step to our coordinates of point vortices by the relations number 2. Now we can try to analyze this differential equation and the new variables, and we can imply some interesting results. The time evolution of pi is governed by the simply Hamiltonian form. This is the not so simple differential equation. P4 not contains on the single slide. And this is the simple differential equation for first order. And we can see that the stationary point of these equations, this not zero multiplier, this is non-zero because P1, P2 more than R square, because our vortices not possible to, has not possible goes inside our cylinder. And with this notation, we have a P1 dot equal to 0 if and only if P4 equal to 0. If we can recalling about what does it mean P4, this is equal to 0 if our point vortices position on the same diameter of our cylinder. And this doesn't mean that no moving Furpel's equilibria for this time. This is strange for the first view, but not strange if we recalling that our total linear momenta equals to 0, because the Furpel configurations moves through our liquids, and that doesn't mean that this case not coincides with the Furpel's equilibria. And there are stationary rotations, only the stationary configurations of our moving two vortices. Yes. Yes, this is the rational functions, but very huge. And now we can see how many times? 1 minute. Oh, can you show me the animation? Now instead our pi, we choose the new variables. These are canonical coordinates. And in these coordinates, we have solutions for the stationary configurations of our cylinder and vortices. This is the cylinder, not moving. And our vortices rotate on the same circles. Another one, please, the second one. This is the rotations of our cylinder and the rotations around it on the circle with the constant radii, our point vortices. And the third one, thank you. This is no periodical motion, is the some kind of simply looks like choreographies of our cylinder and our vortices. And now, can we back to our presentation? Okay. Yes. Due to our canonical coordinates, We have 1 degree of freedom our system. Okay. With this Hamiltonian function in this form. And now we can see the bifurcation diagram with the Hills diagram for this case. First case and the second case, we can see our unstable equilibrium point for each constant of integral of Hamiltonian function and our angular momentum constant. And now another one case when we can see the bifurcate of our equilibrium point, we have 2 equilibrium points at this system. Okay, thank you very much for listening.
We have time for one quick question, please. Well, in that case, it's my pleasure to introduce Dmitry Talalaev from Moscow State University. And Dmitry will talk about graph combinatorics, statistical physics, and cluster algebras.
Much the organizers. It's a great pleasure to be in Yaroslavl each time. Может быть, его сделать большего масштаба?
Потом нельзя будет поинтером поменять слайды.
Is it readable?
Ну, попробуй поменять. Можно. Да, я думаю, что лучше делать так. Не видно.
Нифига не видно.
Да, нет, это нельзя.
It would be better if we can browse like during seminars.
Full screen looks like that.
No, I mean if we can get a file of this talk and we can just browse.
Yeah, maybe if I can share it with you, let me see, is there an option like that? Yeah, so
Сатирис, может, я там буду нажимать на
да, это, да, да.
Если мне нужно кого-нибудь.
Все, давай скажем.
So my talk is about the theory of integrable weighted graphs. But an object itself is a very general object, so it's a graph, just a graph with a set of edges, with a set of vertices, with some function on edges. So this is the weight of an edge. And there is a lot of problem in modern mathematics which looks like which look like weighted graphs. So by definition, it's a point of discrete geometry. So the graph with weights which are distances, for example, it's a discrete geometrical object. So it's an object from many interesting domains in modern mathematics, in Riemannian discrete geometry, pseudo-Riemannian, holomorphic, and whatever. In this setup, this concept is related with the modern approach to quantum gravity, which is called the loop quantum gravity. But I will talk about some other problems. So the weighted graphs appeared naturally in statistical mechanics and what is called the anisotropic statistical models. For example, in anisotropic Ising model, Potts model, in the Dimers model, in percolation problems, which are very interesting, very so up-to-date subject to make mathematics. Up to my knowledge, the same combinatorical and continuous data is related to the world of artificial neural networks. For example, the Hopfield neural network is an example of the weighted graph with properties very closely related to the Ising model, for example. And surprisingly, the same object is related to the modern algebra, to the very modern domain of algebra, which is called the cluster algebras, to formal groups, to n-simplex equation, which are, in a sense, some structural object in the theory of integrable models of many different types. So the principal subject of my talk is the comparison of three models of statistical physics, of the Dimer model, of the model of electrical network, which is also the model of statistical mechanics, and the Ising model and its generalization, the Potts model. All these models possess very important and surprising properties. So each of them are related to some positive Grassmannians. It is another modern object in mathematics, the positivity in the sense of total positivity. So the Dimer model is related, for example, just to the positive Grassmannian. The electrical network in this language represents the positive Lagrangian Grassmannian, and the Ising model is related to the positive orthogonal Grassmannian. So yes, it's a two-dimensional Ising. But you mean it's an Ising model on a graph without any surface structure. It's a combinatorial graph. And naturally, there is some combinatorical problem which are related to these models. For example, the Dimer model, by definition, it calculates, it counts the perfect matching on a graph. The electrical network is responsible to the combinatoric of spanning forests, spanning trees on a graph, and it is not known for the moment what kind of combinatorical problem is the companion of the Ising model. And to each model of these types, there is some algebraical context which is crucially plugged down to this model. It is the solution of the local Yang-Baxter equation and the corresponding solution to the Zamolodchikov tetrahedron equation. I mentioned the algebraic part of this story as the n-simplex equation part. So there is an electrical solution to the tetrahedron equation which is related to the electrical networks, and the orthogonal solution which plays the same role in the Ising model. The same, but a little bit different. So now I'd like to illustrate some of these properties in this table for different different models. And I will recall what is the dimer model. The dimer model, it counts the perfect matching, so the set of edges on a graph which do not intersect, and which cover all the vertices of the graph. So it is by definition the perfect matching or the dimer on the graph. And the statement of Postnikov relates the dimer model with the total positive Grassmannian. So by definition, the totally positive Grassmannian is the set of spaces of the ordinary Grassmannian such that for the metrics which correspond to this Grassmannian, all the minors are positive. So for the first time, it's a strange condition, but it is very, very natural and very fruitful in many different applications. For example, in the Grassmannian of the type 2-4, this two-dimensional space is totally positive because all the partial minors of this matrix are positive. The dimer model is defined on the bipartite graphs. So a graph, those vertices are colored by two colors, and the vertices of different of the same color are not connected by an edge. So this is an example of the bipartite graph, and an almost perfect matching, or the dimer on this graph, is the subset of edges such that the edges of this subset do not intersect, and this subset of edges cover all the set of vertices. So for all vertices in the inner part of the set of vertices, there is an edge which contain this vertex. And now I will illustrate the map from the dimer model to the positive Grassmannian on this example. So example is the same, and here I proposed three examples of the dimers for this graph. So you can verify that the condition are true. For each by P, I define the dimer, and each dimer is supplied by the weight function. So it is a product of weights of edges which take part of the dimer configuration, of the perfect matching configuration in this case. And the dimer boundary partition function is the sum. But one could choose a set of boundary points, and then we define the boundary partition function for the dimer model as the sum over all dimers with the prescribed boundary of the weights of such dimers. And then I illustrated the inclusion of the dimer model to the positive Grassmannian. I calculated all the partial boundary partition function for this case, and it is easy to illustrate that the Plücker identity for this type of quantities is satisfied. So it is really a point of the Grassmannian, and it is a point of positive Grassmannian if all values of parameters of weights on edges are positive. There is a theorem of Postnikov, Talaska, and in fact many other mathematicians from different groups, which states that this inclusion is a map from the set of dimer configuration from the dimer models, so from the set of graphs, in fact, from the weight graphs to the positive to the totally positive Grassmannian. Now I pass to another model and to another property of the model. So in this case, I will talk about an electrical network, which is defined also by a graph. With the function C, it is a conductivity of the electrical network, which is a function from edges to R plus. And we define some partition of the set of vertices as the boundary vertices and inner vertices, and then describe the electrical network by Kirchhoff matrix, which is just defined by conductances of edges. And then we're interested in what is called the response matrix of the network, which is the matrix which relates the currents in boundary points with voltages or potentials in boundary points. In fact, these vectors are related by a linear transformation, and this linear transformation can be expressed from the Kirchhoff matrix as a Schur complement of the block C in this case. But it is a very classical theorem of the 19th century. What is somehow new is our result with Vasily Gorbunov, which represent the same data, the response matrix of an electrical network, in the language traditional in integrable statistical mechanical systems. So in the vertex form. For some simple example of an electrical network, which is just the star. So it is graph with 4 vertices. This one. Here I designed also what is called the medial graph for the initial one. So the initial one is just the star graph with 3 boundary points and 1 inner point. And in this case, we define the response, the boundary matrix. It is not correct, so it is B boundary. The boundary matrix for this network, which is the product of some matrices depending on parameters, which are conductances of edges, and this matrix is given by this formula. And this matrix solves the local Yang-Baxter equation, which is defined by this formula. It is very similar to the ordinary Yang-Baxter equation, but the values of parameters on the left side are different from those on the right side, and this transformation from the parameters on the left side to the right side is given by some rational transformation. And the surprising property of this transformation is that it solves the next level n-simplex equation, the Millionshchikov tetrahedron equation, and it is also the trace of integrability in this model, but the integrability of higher level, of higher homotopy level.
And this transformation is invertible, and the process looks.
I suppose it is involution. And so the statement about the relation between the response matrix and the boundary matrix of this model, which is integrable in a sense, is given by some linear algebraic statement. So we introduce a matrix with 1 on the diagonal, with -1 on the lower diagonal, and -1 here. Another matrix with ones everywhere, and then the statement is the following: the matrix n by 2n defined by the response matrix, and another matrix which is defined by the boundary matrix, boundary measurement matrix, represent the same point in the Grassmannian. So they define the same system of equation related currents and potentials, and this statement allows to reconstruct one matrix from another. So it is the way to formulate the answer to the classical question about the response matrix in integrable terms. And so the principal point in this part about the electrical network model, that there is the vertex representation of the physically interesting quantity in this model. Vertex representation like in integrable systems, in integrable statistical models, which is not present, for example, for the moment in the ISND model. So the last step is some property in the ISND model, and it is a part of our common result with Boris Bычkov and Anton Kazakov. Boris Bычkov will talk during this conference about this topic in more details. So the ISND model is also defined on a graph with the set of vertices, with the set of edge, and with two functions on edges with values in some ring. This model is defined by partition function, which is the sum over spin configuration, the spin, so sigma are spin particle which are placed in the vertices of the graph, and so we sum over all configuration of spins on the vertices with weights which are the products of some functions which depends on the coincidence of spins on the edges, on the vertices of the same edge. So the partition function is defined by this rule. The Gibbs probabilities in this model are defined just by Gibbs weight divided by the partition function. And one is interested by by the two-point correlation function of this model, which adjusts the correlation of spin in two chosen points of the graph. And there is the similar map from the set of ISND model to the positive Grassmannian, but in this case to the positive orthogonal Grassmannian. And another property of this model is the invariance with respect to the star triangle transformation. In a sense, it's a classical result, but so I'd like to explain the fact. And the fact is the following, that if we choose some region of the ISND model, of the graph of the ISND model, with some continuation, and we change this star configuration by the triangle configuration with some change of variables from T1, T2, T3 to the primed variables, and this transformation is defined by this set of equation, then the statement that there is a solution of the local Yang-Baxter equation of this type with the R matrix, which is just the hyperbolic rotation matrix, and with some additional element, the an involution, which is necessary to formulate this equation. So, so my point is that these models are very similar, but some ingredients are missed in some models. For example, in the ISND model, we have not vertex representation for the correlation, for the 2-point correlation function. And the conclusion of this talk, so it is our plan of research of some important group concentrated in this subject, is to find some universal model which depends on parameters, and for different values of these parameters, it gives ISND model, Potts model, percolation model, electrical network model, Hopfield model, or whatever. And for me, it's a good way to produce some integrable setup to the problem of loop quantum gravitation. Thank you very much.
We have time for questions.
And in this Yang-Baxter, also the right-hand side arguments related by invertible involution, or not?
I suppose that with some change of variables, with this involution, the initial transformation from t to t prime is also in involution.
So I want to replace S of T2 by T2, recalculate right-hand side, that this is again rational invertible involution.
Yes.
So what you can say about such type of Yang-Baxter equation in general? It looks very interesting object.
Very interesting, but I suppose it's very strict object. So there is no many solutions of such.
So I believe that it's possible to develop some general theory of such Yang-Baxters. It's true?
I know some paper of Sergey, who is a specialist in such kind of equation. And I suppose its classification, but in some specific case, is complete.
Any other questions? Well, let's thank the speaker one more time. The next talk will be given by an online speaker, Georgy Sharygin from Moscow State University. And Georgy will talk about symmetries of the full symmetric Toda system on real Lie algebras.
I'm sorry, just need permission to turn on my screen. I mean, to share screen. I'm sorry. I need permission to share my screen. So far, I cannot share my screen. That's the problem.
How can I enter the groups? Maybe. Okay. Here it is. Here it is. So I was thinking. Gosha, we made you an administration of the conference. Maybe you could record your talk as well.
Yeah, sure, you can record it.
Yeah, thanks very much.
Of course, that's not a problem. I just, okay, now I can, go on.
Now you have the right to share and do whatever you want.
Yeah, here it is. Here is my screen. Do you see it?
Great, thanks very much.
Yeah, great. Just a moment. I need to change the mode to the full screen. Okay. Okay, is it okay now?
Yeah, it's absolutely fine.
Okay, just turn on my... Shall I begin now? Yeah, it is 12:30, so it's time to begin. And it's a great pleasure for me to have this talk. I'm sorry I didn't come in person to express my deepest gratitude to the organizers. You see, the problem is that I'm a little bit afraid of traveling, so that so many of my friends are now ill or have been ill, so I just prefer to stay at home. I really hope that next time you have this conference, I'll be able to make it to Yaroslav. I like the city very much, and I've been many times there. Okay, so my talk is a report on the work in progress joined with Yuri Chernikov and Alexander Sorin from Dubna and from Moscow Institute of Theoretical Experimental Physics. Yuri is from this institute, and it is dedicated to the study of the full symmetric Toda system. So I believe that everyone, or almost everyone, knows what is the usual symmetric Toda system. But as far as the full symmetric Toda system is concerned, that is probably not so wide known. Okay, just need to know how to scroll. That's a problem. Sorry. Need to, oh yeah, here it is. So, no, it doesn't work. Oh, no. Okay. I'm sorry, I'm not used to making this talk with my slides and with online at the same time. So I'm probably not a little bit clumsy. Yeah, here it is. So the full symmetric Toda system is a system we obtain by considering not tridiagonal matrices, but arbitrary symmetric matrices, L, the X matrix, and by considering the equation L dot is equal to the commutator of L and A, where A is a naive anti-symmetrization of the matrix L. When you commute symmetric and anti-symmetric matrix, you obtain a symmetric matrix again. So this equation is perfectly well understood. It works nice, and you can now consider the properties of this dynamical system and check if it is, say, Hamiltonian and whether it is integrable or not. Okay, there's know how to scroll. So next slide. Up. Oh, here it is. So I'll probably turn off my tablet. I try to use tablet, but probably it's not the best idea. Sorry for this. So here it is. Now, the system turns out to be both integrable and Hamiltonian. And as far as Hamiltonian property is concerned, it is easy to see. Actually, just pull the Poisson structure from the co-adjoint representation of the space of upper triangular matrices by using Killing form to identify the space of symmetric matrices with the space of upper triangular matrices. But as far as the integrability is concerned, it isn't so easy to see because, of course, if you look at the previous slide, how do you go from one slide to another? Oh, here it is. Yeah, here it is. So if you look at the previous slide, if you look at this equation, and of course you see that trace of the matrix L and trace of any power of the matrix L will be preserved by this equation, but these integrals, these first integrals, the traces of powers of L, are not enough to ensure the integrability of the system because there are much more degrees of freedom than just n variables can provide us. So we need to look for additional first integrals. And it turns out that there exists such a set. For instance, one of the most popular sets of first integrals is given by a so-called chopping procedure, which was first discovered by Lee, Nand, and Tomei. namely take the matrix L, subtract the identity matrix times lambda, and cut off the first k rows and last k columns, so that initially what you obtain is a very strange matrix with lambdas on some not some additional diagonal. Then you compute the determinant of this matrix, and you obtain a series of polynomials which appear before the powers of lambda, and then you take the ratios of these polynomials. So these functions fkp, they are rational functions, and it comes as a piece of surprise that these functions not only are preserved by the equation, but they actually commute with each other with respect to the Poisson structure I just described. So in what follows, I try to find a geometric way to find such symmetries, such additional integrals in case of full symmetric Toda system, although I must admit that the construction I'm going to describe does not give complete answer to this question, but at least it gives some additional set of first integrals, probably not Poisson commuting first integrals, unfortunately. So in order to do this, well, probably it would be convenient if before we proceed with the construction, we use some generalization of the construction, and it will probably be more understandable how to do this. So we consider arbitrary real Lie algebra, real form, not necessarily split real form of a complex semi-simple Lie algebra. Then we can find a Cartan decomposition of A, so that K here, Gothic K, is a maximal compact subalgebra, and P is algebraic complement of this subalgebra. Then we have this set of commutation relations. As you see, P is no more a subalgebra. But P is a K module. And it is precise in the case, sorry, there is some noise. Can I go on? I don't know, probably someone has turned on, has forgotten to turn off his or her microphone. Okay, I'll go on and ignore it. Okay.
You are the host, Georgi. You can turn him off.
Sorry?
You can turn him off. You are the host.
Yes. I can turn him off.
Just turn him off.
Yeah, sorry. Yeah, sure. That's what I'm going to do then. So this is yeah, Justin M. I'm sorry, I turned off sound. Yes, I'm the host. I forgot about this. Thank you. Okay. Do you hear me? Okay, I go on. So here is the series of here's the commutator relations. As you see, K is subalgebra and P is a K module. So it's precisely the case when K is the algebra of antisymmetric matrices and P is the module of symmetric algebras or symmetric matrices. So you can always imagine that K is just this and P is just this. But it is convenient to have this general point of view probably, because you will see that it will work much more general case than in just case of symmetric matrices. Okay, so then we choose maximal commutative subalgebra in P, let it be H, and then we can find a system of roots inside H star, so that we have the composition of our Lie algebra G as the sum of H plus upper and lower nilpotent subalgebras. So in terms of the roots, we have the composition of K as the sum of all positive roots of the expressions, the generator of positive root space minus the generator of negative root space. And P will then be equal to the diagonal submatrix, the Cartan subalgebra, plus the sum over all positive roots of EA plus E minus A. So this is precisely the analog of anti-symmetric submatrices, matrices, and symmetric matrices. Okay, we go on, and then we have the generalization of the symmetrization map, of naive anti-symmetrization map. So naive anti-symmetrization map consisted of taking the upper triangular part and subtracting the lower triangular part of symmetric matrices, metrics. So here the symmetric matrix is just L. It is just an element in P, right? And then the anti-symmetrization, the naive anti-symmetrization in this language is just given by taking the same, removing X from our matrix, and then taking, instead of the expressions EA plus E minus A, the expressions EA minus E minus A. So that's the counterpart of the naive anti-symmetrization. So everything works perfectly well. I'm going to consider the full symmetric Toda system on G. So that is the object I'm going to talk about. So this system is again Hamiltonian. Actually, you can once again pull the Poisson structure from B plus to P using the killing form, and then take the Hamiltonian function given by the trace of the adjoint representation of our element. Okay, but that's not the main point of my talk. The main interest for us is the following observation. It turns out that instead of this system, we can actually consider a vector field T lambda on the maximal compact subgroup. This maximal compact subgroup K of G acts on the space P. And it turns out that the evolution of our system can be described in terms of this action, of the action of the maximal compact subgroup. Namely, we can consider the vector field on the group K given by this formula. That is, we choose an element in H in terms of the matrices. We choose a diagonal matrix, lambda, and we take the adjoint action of the maximal compact subgroup on this diagonal matrix, on this element of Cartan subalgebra. This will, of course, take us away from the space of diagonal matrices in general, but then we can, but we will not take us away from the space of symmetric matrices. And then we take this naive asymmetrization map M applied to the result of this adjoint action, and this will be the value of our vector field at point K. So now, if we take the trajectory of this vector field, let it be L of t, let it be K of t, then the trajectory of this Toda system on P can be described as the adjoint action on lambda by the trajectory of this particular Toda field. I'll refer to this field T lambda, T sub lambda, as the Toda field on K, and it is this field which will be the object of our prime interest in what follows. So I will totally replace my Toda system on P by this Toda field. It is more or less the same thing for me. And I'm going to describe invariance of this Toda field in what follows. Okay, I'm going to skip this for a while. Okay, this is just an explanation why this is as good as anything else, but it is not what I'm going to pay attention to. Okay, and now, in order to understand this construction, I need to regard N projection from G to the space K along the space of lower triangular matrices B minus, or we can also call it the space of all lower Borel subalgebra. In invariant terms, it is lowest Borel subalgebra. And this actually, this identification of M with this projection explains why the vector field, why this map M has so many good properties. You see, it appears here, and one can wonder if one can take any other map of the same kind. There are much more than just this kind of projection from symmetric to anti-symmetric. However, it turns out that this particular projection is very nice because it is can be identified with this projection along B minus, and it is because in case when there is a decomposition of Lie algebra into as a sum of two Lie subalgebras, and this kind of projection verifies this Nienhuis equation. You see, this Nienhuis equation is a quadratic equation on M, and it appears in geometry in many particular cases. For instance, it appears in as far as I can remember, in Nuremberg, Neulander's statement about the complex structures and manifolds and many other places as well. So these Nienhuis equation and Nienhuis structures are important structures in mathematics. So it's not a wonder that the fact that M is a Nienhuis map proves helpful for us. Namely, consider a generalization of the vector field T lambda. So T lambda used to be the vector field which was generated by lambda when we took the joint action of group K on lambda, and then we projected along B minus to anti-symmetric space, and then we pull this along K with the help of right translations to the point K. So it turns out that now I can do the same trick with arbitrary vector in the algebra G instead of just taking the diagonal matrix. And we obtain in this way a set of vector fields Tx on the compact subgroup. And as a kind of surprise, but probably not a big surprise, we have that these vector fields constitute a representation of Lie algebra G on the group K. So here is the explanation. You just take the commutator, and then present this commutator as right translation of some element Z. And then you compute this element Z, and it turns out that because of this Nienhuis equation, this element Z is equal to the joint action of K on the commutator of X and Y. So we have this. And a very interesting particular case, one can consider the group G, the algebra G, being just the algebra of 2 by 2 matrices without trace. Then the compact subgroup will be just the group of just a circle, with just SO2. Then we have these kind of commutator relations. And if we perform all the computations, we'll see that the vector fields E, F, and H, which we look for, have this form, where A is the standard parameter on the circle, and it goes by a straightforward computation now shows that all the commutator relations hold. So now we have a representation of G on the group K, and of course, if two elements X and Y commute in G, and the corresponding vector fields will also commute. In particular, we can take a very large commutative subalgebra, and then we can obtain a large family of commuting vector fields on G, much larger than just the n diagonal, the vector fields which are generated by the traces of lambda. various lambdas, right? The problem is that these vector fields need not commute with the vector field T lambda, and that is actually our purpose, to find these vector fields so that they will commute with T lambda. That will be the symmetries of the Toda field. That will be the symmetries of the Toda system. That is what we are looking for. And if we take, for instance, X to be an element which is the base of a root space in the algebra G, then the commutator with T lambda will produce not 0, but will produce Tx up to a constant term, a term which will only depend on X and on lambda. It is nice, but it is not 0. In order to take care of this, we can multiply our vector fields Tx by certain functions f, which will so that these kind of relations should hold, and then it is easy to compute that the commutator of T E alpha times F alpha with T E beta times F beta will be still 0 if E alpha and E beta commute. But also the commutators of these fields with T lambda will also be 0, because T lambda will produce minus, say, B lambda times F of F beta. Sorry, minus beta lambda times F beta. Whereas commutator of T lambda with T E beta will produce plus beta of lambda times the same vector field. So these two terms will cancel out and we'll get 0. So now the problem is to find a good set of functions, and here we can use representations of the V algebra to our advantage. And here's how we do it. We find the lowest weight representation of the V algebra. Lowest weight means that there is a vector V minus such that all the elements which correspond to the negative roots will kill this element V minus. There is the elements in Cartan-set algebra H will act diagonally on V minus, that is to say they'll multiply this V minus by some weight functions. Though morally speaking, it is the same as the standard representation of the special linear group or special linear algebra. There you can take V minus to be the vector which has zeros everywhere except for the last element in the very last term, right? Except for the very last element in it. So all the lower diagonal, lower triangular matrices will kill it, and only diagonal matrices will give something non-zero if you take lower triangular. Okay, so we have a lower weight representation, and then we consider the functions. I think here it is. Sorry, F minus, where is it? Sorry, I think I missed this. Did I? Yeah, I'm sorry. I think I need to turn on my tablet to write down the definition of this function, because I think I missed it when I prepared my talk. So here is the definition of the function. Okay, so f rho minus comma I applied to k is equal to the scalar product of rho of k. So actually we integrate the representation of the algebraic representation of the group G and restrict it to the maximal compact subgroup in it. Then we apply it to the ith vector, ith basis vector in it, and then compute its pairing, scalar pairing with the lowest weight vector. Actually, it constitutes just the lowest row in the matrix, which represents the matrix of representation of K. The lowest row, the element in the lowest row of this representation. Is this clear? I'm sorry for having forgotten about this. I think I missed this slide when I prepared my talk. Okay, so now it is easy to compute that when we apply T lambda to this kind of functions, then what will survive will have this form, you see? So it will be equal to the product of this function with will be equal to the product of this function. So where is it? I'm sorry. Yeah, here it is. It will be equal to, if you compute this, it will be equal to f rho minus I times omega 1 of lambda, I think, minus some function g, which will depend on k, of course, but only on the representation. It will not depend on I, which is actually a very important thing. So it means that if we take two such functions and take, for instance, their ratio, then this function g rho, which doesn't depend on I, will cancel out, and the only thing which will survive will be the difference of these two weights. And the difference of the weights is equal to a root of the group of a Lie algebra, and that is how we shall use this. Okay, I'm going to the next slide. Okay. Yeah, here it is. I think this is this computation. Yeah. This is this. So we have this function here. And when we take this, so when we apply T lambda to this ratio, we obtain this kind of expression. And in particular, if we take suitable ratio of these functions, we obtain just an invariant function of our dynamical system. And in this way, varying representations and varying the elements I, J, and KL, we obtain a very large set of representations, of invariants. For instance, in case of usual symmetric matrices of the usual Toda system, we obtain various minors of the matrix K as ratios of minors, actually, as invariants of our Toda system. So this is it, more or less, because now we can modify a little bit our construction to obtain the functions by which we can take multiply the field T to ensure that it will commute with T lambda now. Namely, here's this description of this construction. First, we compute the action of the vector field Tx on this kind of function. It turns out that we also have very similar formula, namely the first term here only depends on x and on rho. It doesn't depend on I, you see, it has to depend on function. So if we are sure that this is 0, which only depends on representation, on the choice of x and the representation, then taking ratios of these functions, we shall obtain the function we really need. Sorry. Yeah, and in this way, we finally come up with a very large set of vector fields on the group K, which will commute with each other and which will commute with the Toda field lambda. Sorry, this should be capital T, not script T. I'm sorry for this. Yeah, so this is more or less the construction. The only thing I really need to tell now is that, unfortunately, I cannot prove that the vector fields T rho we have just described induce Hamiltonian vector fields when we transfer them from the maximal compact group to the space of symmetric matrices. And on the other hand, it is known that the vector field T lambda is in fact not Hamiltonian. It is gradient vector field on the compact subgroup. So probably what we should really look for is to answer the question if the vector fields T rho, which we have just described, gradient vector fields or not. So this probably will work better. In fact, the interplay between Hamiltonian and gradient properties of the vector fields is really very intriguing in this context. And for instance, it helps one to describe the properties of the dynamical system itself. For instance, to show that the phase portrait of Toda system, of the full symmetric Toda system, coincides with the Bria order on the Weil group of Lie group, and so on. I think I'll stop here.
Time for questions. The lunch break is for 1 hour, so
I'll try to squeeze into the
let's thank
30 minutes.
Last question. Is it correct that this full Toda lattice, full Toda system is a kind of extension of open Toda system, which correspond to simple algebras, not to fine algebras like periodic Toda systems?
Yeah, of course. The periodic Toda system is is different case.
Yeah. Generalization of this picture is away from periodic Toda system.
Oh, it is really very interesting. I know that some of the properties of the usual Toda system can be transferred to the periodic Toda system. In particular, for instance, one can show that periodic Toda system is also induced by a gradient flow on some fancy infinite dimensional Lie group. But for instance, if you want to combine both this full symmetric Toda system and periodic Toda system, then have never seen such a construction. The tridiagonal generalized.
And the second question, so you have plenty of invariants and commuting vector fields. Is it sufficient, from the point of Lie theorem or whatever, for the integrability, in quadratures?
So the problem is that in different cases, the number of invariants you need to ensure the integrability is different. So far, I can only say that the order of the quantity is sufficient. Namely, the order of invariants you need to ensure the integrability of full symmetric Toda system is proportional to the square, to 1/4 of the square of the size of the matrix, because actually it is 1/2 of the dimension of the space of symmetric matrices, and the space of symmetric matrices is, as far as I can understand, remember, n times n minus 1 divided by 2. So we need about n squared divided by 4 commutative elements to ensure the integrability in this case. And if you look at the construction, you'll see that the maximal commutative subalgebra in SLN is given, for instance, by the span of this upper right angle of the matrix. So the size of this is also proportional to n squared divided by 4. And of course, we need to find representation rho, which will ensure that it will commute with t lambda. But that is more or less technical. So we just look for some particular cases. That's, yeah. So how to say, the order of the asymptotic of the size of this space of commutative vector fields which I have just described is correct. However, I cannot swear that it is totally what we need, because I cannot even prove that they are Hamiltonian. See, that's a pity.
Well, for integrability, you don't need Hamiltonian in the Lie theorem. So you can do it without Hamiltonian structure. You need just commuting or flows or so.
Yes, they are commuting flows, but they're commuting flows on compact subgroup. And if we look at the definition of chopping, you'll see that chopping give you Hamiltonian commuting flows on symmetric matrices. So the problem is if we can actually match these chopping flows with the ones which I have just described or not. And that is really very, very difficult to say. Direct computations show that they're pretty close, but not quite the same. Direct computations with symmetric matrices. They give very similar equations, but not quite the same equations, unfortunately.
So any idea about the quantum picture for these systems? Anybody? Oh.
That's quite that's a totally different. I would love probably to see this kind of construction probably as much as you do, but so far not.
Okay, thank you. Very interesting, thank you.
Okay, Gosov, thanks very much again.
Yeah.
So
thank you for inviting me. I'm sorry I couldn't make it to Yaroslavl this year. I think like 7 years ago, I used to go to Yaroslavl twice a month.
We're organizing conference every year. We will invite you again next year. Don't worry.
So probably next year when the pandemics will be over, sure. I'll be able to visit you.
Just a technical thing. I gave you administrator
sure.
rights.
What should I do now?
Could you please give it to me back? So you
just
see me in the
moment.
list and you make me administrator.
The sharing my screen. That's the first thing I need to do. Next, I need to go to the participants and make you.
So if you find me in the list, there is.
Yes. I'm looking for. Make you the organizer. Yeah. Thank you. Bye.
Thanks very much. Thank you.
Now you're the organizer.
Yeah. Thanks very much. Thanks again for your talk.
So
we continue at 2:00 Moscow time.
Okay. Goodbye and see you in an hour.
See you soon.
talk about the growth of characteristic Lie-Reinhart algebras of hyperbolic.
First of all, I would like to thank organizers for invitation here. I told already to some of my colleagues that it's absolutely a fantastic place here. It's Tensor, so the facilities here is incredible and very interesting to watch what's happening inside this building. And so it was, I don't know what was the initial idea to organize here to find this cooperation with Tensor company, but anyway, I think that it's a wonderful example. If we cannot compare, and even in Moscow we have no such facilities for organizing conference. So thank you again for this invitation. And second remark is, it's wonderful. A few days ago I came back from Grozny, and here again I saw a lot of my friends, colleagues, that were participants of two Kazinoy Arm conferences in Chechnya Republic. It was 3 years ago, and it's very nice to meet all of them here in Yaroslavl. And now I am going to tell maybe some results that are in the domain between integrable systems or pure algebra. Just the initial idea was just to understand some proofs or definitions from texts by Shabat, Geber, Sokolov, that there is some gap between the pure algebra and mathematical physics. I think, yes, it's some risky statement. However, there are a lot of, for me, were unclear points in some text concerning characteristic Lie algebras. So that was the original setting. And the first one, here, sorry. So just briefly recall basic definitions for today. So the important notion of growth of infinite dimensional Lie algebra. So we suppose that our Lie algebra is generated by some finite dimensional subspace here, V1. Then we consider all commutators, so we can consider like an alphabet, or you can take a finite basis in this subspace and consider ordinary brackets, commutators. And this will be together with initial alphabet. If we add commutators, will be subspace V2. And then we continue, and the nth subspace is elements that can be represented as commutators of length of at most n with arbitrary arrangements of brackets. And there are now huge number of activity concerning the growth of algebras, not necessarily algebras, associative groups and so on. There are interesting relations. So here is just very, very brief version. I took as an example the definition of a popular characteristic that is called Gelfand-Kirillov dimension. This is formal definition. You see this as some limits, logarithms, but non-formal meaning is if you consider the formula for dimensions, it can be, here it's of course equality in some non-formal sense, behavior like constant n in power alpha. And this is, this denominator is, in fact, if exists, finite denominator, our power is
Gelfand-Kirillov dimension, so the asymptotic behavior of your dimension. And finite Gelfand-Kirillov dimension means that your growth is polynomial in this sense that dimension of all elements, I recall that represented of length at most n, less is restricted by some polynomial Pn. So we call this situation polynomial growth. And of course, some natural examples. The fastest growth is of free Lie algebra. If we have m generators, here this is behavior. And also if we consider another pool of growth, the slowest growth, that is interesting for today, is very simple Lie algebra, positively graded. Here is basis, infinite basis, E1, E2, and so on. And here I put only non-trivial commutation relations. So we have only non-trivial commutative relations with E1. So E1 shifts each basic element by 1 to the right and nothing else. All other relations are trivial. And it's easy to see that the behavior of function is n plus 1, and so in natural arguments is the slowest possible growth of your infinite dimensional Lie algebra. Of course, you can don't forget about finite dimensional case. It's also you can put in this situation. But if you deal with infinite dimensional, today we also use some additional structure in our algebras. I mean, all of them will be graded. And special attention I'll pay to positively graded Lie algebras. So you see that down scripts that mean the grading of your algebra, and this is graded by natural numbers, not by integers. So it's very important restriction, as we will see. And if we, in fact, the growth function is not well defined, because I mean the dimension of the subspace VM. You should define it up to some equivalence relation. I skip this accurate definition. But in the case of, in the case of positively graded, and natural graded, one can define so-called homogeneous growth function, special, because you see from this definition it follows that your Lie algebra is generated by G1, the first component. So it follows immediately that dimension of G1 is greater or equal to 2. Otherwise, you'll have some trivial. And it's easy to see that the growth function, I mean dimension of the corresponding subspace, sum of dimension of homogeneous subspace. This is very special, not general situation. Now, if we read some literature concerning the relations between growth and integrable systems, the first, they appeared at the time that were very famous at that time, very, how to say, important Ka's theorem, later that he transformed to his conjecture, that about simple infinite Z-graded Lie algebras of finite growth. Again, you see, this is again some polynomial which is a bound for dimension of Gn, but important feature is here is your Lie algebra is Z-graded and simple. This is very serious restriction. I mean difference between positive grading. Because in positive grading we have no simple objects for trivial, like nilpotent case, no simple objects. And his result was that if we take consider this restriction, we have only 4 classes of algebras, so-called loop algebras or Kac-Moody algebras. So this is, you see that simple Lie algebra stanzed by Laurent polynomials with respect to one unknown t. So-called twisted loop algebras, more complicated definition, I'll skip the detail. Again, another type of Kac-Moody algebras. Classical Cartan type Lie algebras, so Hamiltonian, so polynomial vector fields. And himself, Katz, under some additional conditions, proved that first 3 cases he included. But if you drop off this technical condition, doesn't matter what it is, one should add the only one algebra with algebra. And that was the results of well-known Olivier-Mathieu theorem with very interesting proof. And sometimes when people in this, in thinking about growth Lie algebras, this theorem maybe plays an important role, but I would like to say that it's not the case for in general situation. If you consider really growth of Lie algebras, you should consider other cases. And the first result showing that this is huge is a distance between 2 types of Lie algebras, Z-graded and N-graded cases, that if you consider even 2 generated Lie algebras, but positively graded, naturally graded, you remember that definition, even with this restriction, this is slow linear growth. You see, with this condition, even in this situation, we have continuum pairwise non-isomorphic Lie algebra. So a huge number of algebra. And if you compare with Katz result, this is, you see that all this, if you consider union of all these cases, is countably many Lie algebras. So this is really 2 different universes. And now again, it's now a part of some, how to say, methodological, that when I started to understand this famous book by 4 authors about characteristic, it's called characteristic Lie algebras, Lie rings. And I remember the formal definition of Lie ring, and I found something strange because I mean, it was kind of a generalization of Lie algebra when you can consider multiplication by your elements by some functions, not by constants. But I suppose that this is should, and now Habibulin, for instance, and his scholars use this definition, you should say Lie-Reinhart algebra instead of Lie ring, because Lie ring is something, of course it is generalization, but it's another object. And this is idea when you, or sometimes it is called Lie-Reinhart part. You see that is 2 objects here, Lie algebra and some commutative algebra R. You can consider complex number or real numbers. And you have relations between 2 objects. First of all, your Lie algebra X by derivations on your commutative algebra A. In this way, it's just definition of derivation. And you can also multiply your elements from your Lie algebra by elements of this commutative Lie algebras. And these relations, quite natural. And why they are natural, we'll see next example, the main example, which maybe is cornerstone of all this stuff, is algebra of vector fields on manifold. So you have Lie algebra, infinite dimensional algebra of vector fields, and A is all smooth functions on your manifold. And of course, you can multiply your fields by functions. This is our operation. And then your vector fields in local coordinates, you see formula X on functions on your manifold. No, of course, no. Yeah. It's an initial example, yes. The next example, when you consider some polynomial Lie algebra, some polynomial with unknowns T1, T2, Tp, and we assume today we deal with graded case, so we can introduce weights or grading of generators, putting some weights for generators, and in a natural way define your grading is in a standard rule. And this type of Lie algebras, it also was the aim to understand when Viktor Matveevich gave first talks, what is polynomial Lie algebras. It was for me very strange, but I think that is, in fact, a special example of Lie-Reinhart algebras with additional graded structure. So your Lie algebra should to be graded, as well as your, of course, we define the grading of your associative polynomial algebra. And this is conditions of compatibility of two gradings. Quite natural. And exactly that he introduced the study situation when your algebra is a free RT1 module. And in this situation, your structure relations, you see that looks like Lie algebra relations, but now here it's structure not constants, but structure polynomials. That is another way to write your commutating conditions. But you should also to add how your basic fields act on your coordinates, on your unknowns TQ. So this is also the double set of polynomials. Cij polynomials in this algebra, and as well as Viq. And all of them are homogeneous, so the first and the most elementary example is if you consider rank 1 algebra. So you have only one, you see, unknown T, and we define weights, gradings of your elements set by 1, and the relations are the following. Of course, what is the definition of rank 1? It means you have only one basic elements with respect, of course, to multiplications by your commutative algebra. And important thing, you should define how your basic field L acts on elements of your polynomial algebras. Here I put this as natural L of t set equal to t squared. And it's just, how to say, just tricky, simple observation. This is, in fact, we know this is positive part of the Witt algebra, represented in this sense. So this is not, of course, something deep observation, just the most elementary example. And natural question whether your polynomial algebra always determined by some representation as derivation. Simple, another example. One can consider trivial action, again rank 1, rake 1 case, and commutator of rank 2 two generators, L1, L2 equals T by L2. And this is a representation by means of Lie-Reinhart pair of Lie algebra that we already considered. Remember the slowest possible growth. This is Lie algebra of this type. And this is the way how to produce the basis of this Lie algebra. And of course, it's quite natural. Sergei Petrovich Novikov said that no sense to prove evident propositions. However, algebraically, it was useful, I think, to stress that if we consider examples that generates two last examples, all these Lie algebras produced in this way have at most polynomial growth. It's quite natural to expect this result. However, this is first theorem that I would present. And what is the relation to integrable systems? I just was intention to understand the conjecture, how to prove or disprove in general setting with integrability of hyperbolic systems, continuous discrete implies that your characteristic now Lie-Reinhart algebra has slowed growth. And I again stress that it's not Lie-Ring. It's Lie-Ring. It's different object in gel algebra. Habibullin, I'm not sure that in the book there were references to two Habibullin papers, but I suppose that it was conjecture was maybe in some Geber school, Sokolov. So that's okay. So next time I took this as what's preface of the book, so it was the source. So it's useful for today. And unfortunately, but I started 5 minutes later, so maybe I have 5 additional minutes. So just briefly recall of definitions, the notion of characteristic Lie algebra came, this is Gursa method for finding, for looking for integrals of equations. So just briefly recall, but I suppose everybody here knows this definition. I'm newcomer in some sense. So the algebraic way how to simplify calculations, if you replace your partial derivatives of this type by different coordinates u1, u2, and so on. And then if you compute partial derivatives with respect to y, you have simple expression. And for me, it was who is more algebraist than physicist, that if you have sum of two numbers, that sum equals to 0 if each of them equals to 0. However, here you two parts, so if these first partial derivatives vanishes, so it's 0, and you rewrite all these terms, infinite number of terms, as a special differential operator. Here it is, so with new notation D capital. And if your operators, if function f annihilates two operators, you have x integral of your, for instance, here is Klein-Gordon equation for simplicity. There are some very elementary algebraic rules for computers, and here are some just examples what are coefficients for your differential operator. You see this is d squared, d1, and the operator that we are studying is here. So I just present here the next coefficients. And very simple calculations, so that if you consider commutator of two operators, it is the same operators when you consider instead of function f, its derivative with respect to U. And very simple example, Liouville equation. If you consider Liouville equation with this function, then you see it's like definition, exponential function that commutators give you the same function, and the subspace is two-dimensional. And now I'm not considering Lie-Reinhart, in fact, honestly speaking, algebra, but Lie algebra call generated by two operators. So x here. Next, a very important example, sine hyperbolic sine Gordon equation for simplicity. You see that here in this situation, if you consider the commutator bracket, it will give you cosine hyperbolic function. And if you consider, however, span of two operators, your operator for add x0, it's invariant subspace, two-dimensional subspace, and it's diagonalizable operator, and corresponding, it's better to more convenient to consider instead of sinus, sine, and cosine exponential. Here you see it like in a classical situation. And here it's a nice representation because the coefficients, polynomial coefficients, so-called Bell polynomials. So here some first examples, well-known object in combinatorics. And important observation that what missed in literature, then if you compute brackets in this convenient basis, you will get immediately very simple, well-known at the same time relations of that is are in loops of SL2K. So the Lie algebra generated by two fields is in fact isomorphic to positive loops that I denote by N1. It's nilpotent subalgebra of loops. One can consider a generic case. So consider the linear combination of two different exponents with different lambda 1, lambda 2. And it is more convenient to define your, not instead of two generators, consider three generators of your Lie algebra if you want to compute the dimensions. And all elements generate, all Lie algebra generated by second and third elements that are eigenvectors for x0. It's very simple structure. So the growth of the whole algebra is determined, in fact, by the growth of commutant, of its nilpotent part, absolutely determined by this. So you should consider, in order to find this, of course, it's not my idea, it was long ago, just I want to, it's very simple thing. And again, that if you consider second integrable case for Klein-Gordon equations, Tseka equation, your Lie algebra is now related to the another affine Kosmody Lie algebra of so-called twisted, twisted positive part of twisted A22 algebra. And now we already introduced. No. It's not my. I cannot. I know this is classical result by Shabbat Ijeber, and I only study the growth. So this is just relation to growth. I see Satiris. My time is almost over. So maybe yes, it's the last slide. Maybe another result. The second theorem of my talk is my PhD student Fedor Pokrovsky. And it's natural question to consider Lie algebra generated by generic situation with the generic lambda. And his result is if this ratio is arbitrary non-algebraic complex number, your Lie algebra is the free algebra generated by two elements. Just to stress attention that it is not absolutely trivial. It is quite natural result, but not trivial. I just recall, maybe, I'm not sure, the first Maksim Kontsevich result when he was a student by Alexander Kirillov. He published in 1983 the paper called The Growth of the Lie Algebra Generated by Two Vector Fields on Real Light in Vestnik MGU. And if briefly recall his result, if you consider two vector fields on real line, you see only with ion coordinates. So it's defined by two functions, gx and rx. And it's never isomorphic to free Lie algebra. That is absolutely, for me, very surprising result. And even for generic case, we have so-called intermediate growth, not polynomial, not like in free algebra. So some estimates, and it is, however, complicated. And the ground that there are some relations in this Lie algebra. That's why it never cannot be free algebra. So this is just illustration why this theorem is not completely trivial. So I stop here. Thank you, and sorry for delay.
So there is some time for a very quick question.
You defined the characteristic algebra for Klein-Gordon equations. Is it possible to define characteristic algebras for more general equations?
Of course, here is the author of this definition here, Vladimir Sokolov, but I just conjecture, but definition, conjecture also. So here I just, no slides. Yes, there is this definition, but Klein-Gordon is the most simplest case. In general situation, you should consider two characteristic Lie algebra. If you have dependence of your right-hand part on partial derivative. Hyperbolic. Hyperbolic. Hyperbolic.
And for higher order equations?
And for systems also, yeah.
Only for the two,
Yeah.
not higher. What do you mean order? With respect to derivatives.
Just I want to come back. Where is our...
We should discuss. I think we are speaking about different concepts.
Maybe, but I miss here the definition of Klein-Gordon equation in my slides, so that's why it was the pause. Yes, there are generalization, and the open question, Vladimir Sokolov, I remember talk 1 year ago that he again stressed attention for some a lot of open questions concerning more general case. When your function f depends right-hand side of your equation, u x y equals f depending not only on u like in Klein-Gordon, but partial derivatives u x, u y, and so on. Yeah, this means there is a notion, but it's more complicated. I mean, you should consider maybe symmetric case. There is more suitable, but here I again recall that it is completely algebraic questions. It's not the study of specialists in integrable system. Like the way to understand from algebraic point of view, pure algebra, what's happening with this stuff. This was my initial intention.
Okay, thank you very much. Okay, thank you very much. Thank you. So the next speaker is Vladislav Sidorenko. 1 second. PowerPoint. So the talk is about retrograde coorbital motion of celestial bodies, the investigation of qualitative properties using wisdom's adiabatic approximation. So please.
Title of our conference is Integrable Systems and Nonlinear Dynamics. And contrast to previous talks, which were devoted mainly to problems of integrability, I will consider a problem related to nonlinear dynamics. More exactly, I suppose to consider one problem from celestial mechanics. In my talk, I suppose consider so-called resonant motion of celestial bodies. Here I present the outline of my talk. I suppose to give the definition of resonant motion. I suppose to consider and to say some words about methods used to study them. Two celestial motion, two celestial bodies moves in resonance, in so-called mid-motion resonance, if the ratio of the periods is close to ratio of two small integer numbers. Here I presented some examples of mid-motion resonances from the dynamics of real celestial bodies. One example is related to the motion of exoplanets, planets which move around the... Sorry for bothering, I think your microphone is off. Sorry, your system is Hamiltonian? Hamiltonian. Okay. And the second example is related to the motion of one of the families of asteroids in our solar system, so-called Hilda asteroids, which are in a 3-to-2 mean motion resonance with Jupiter. Okay. How to study mean motion resonance? Mean motion resonance were investigated by many specialists, and in a textbook on celestial mechanics can be found different approaches to investigation of mean motion resonance. But I should say that for long enough time, specialists considered only the cases when motion of celestial bodies close to the circular motions, and this motion considered in a considered as a motion with a small inclination, in a motion in a planes which are close to each other. In many cases of resonance motion which were discovered recently, this assumption is not satisfied. For this reason, and new methods were developed in last decades. And in my studies, I used so-called wisdom approximation, which was proposed by American specialist in celestial mechanics, Jack Wisdom, 35 years ago. And different generalization of this approach were proposed lately. So, I should say that we are living in a time of great astronomical discoveries. In particular, the number of neon small celestial bodies in our solar system increased from approximately 20,000 to approximately 1 median in the last 3 decades. And many of these recently discovered celestial bodies move in very exotic orbits. In particular, I would like to attract your attention to so-called retrograde orbital motion. If somebody put a look on our solar system from the so-called north pole of ecliptic, then he will see that most of celestial bodies moves in the same direction, in a counterclockwise manner. But there are several celestial bodies which moves in opposite direction. There are several celestial bodies which are in a so-called retrograde orbital motion. The number of these bodies is small enough, and first such a body without evidences of combinatoric activity was discovered only 20 years ago. The first asteroid in retrograde motion was called Dioretsa. It's the word asteroids written in reverse manner. And now we know approximately 100 objects in retrograde orbital motion. And what is curious, some of these bodies in retrograde orbital motion are in resonance, in a retrograde resonance with the giant planets. And the most curious case is the so-called coorbital retrograde mean motion resonance. So it's the case when two celestial bodies moves approximately the same orbit, but in opposite direction. And resonance prevents the collision. And now I would like to demonstrate how the motion of these, how the properties of this retrograde coorbital resonance can be investigated using the method of modern Hamiltonian theory. So, to write down motion equation in a Hamiltonian form, I will use so-called Delaunay elements. These Delaunay elements are some functions of the Kepler elements. On this picture, I present the definition of Kepler's angles. I will be interested mainly in the behavior of so-called argument of pericenter. Is the angle between the line of nodes and line of abscedes. And also I will investigate the behavior, the evolution of eccentricity of the orbit of these, of the retrograde objects which I will consider. And I forgot to mention that we are really now objects in a coorbital retrograde resonance. These objects for a long time specialists use a preliminary designation for these orbits, BZ 509. It moves close to the orbit of Jupiter. Now these objects obtain this name. The translation of this name in English means means a friend of Jupiter who is always in contradiction with him. It's curious that so many English words used to describe what was named by one Hawaiian word. Okay, so the usual procedure to investigate resonance dynamics is described in a book by Arnold Kozlov and Neistat. As usual, we have a process of 3 time scales at resonance, and usually we have a partition of variables at resonance. We have a fast variables. Then we, after the proper change of variables, we can introduce so-called resonant phase, and variation of this resonance phase will give us the second time scale in the dynamic of a resonance system, and the last time scale characterizes a so-called slow process. And after the to investigate the slow process in this system, to investigate the slow evolution of the secular evolution of the celestial bodies orbital elements, we apply two averaging. First averaging is over the orbital motion, and after that we will have, after the first averaging, we will have only two time scales in this system. We can forget about the fast processes. And the second averaging, for the second averaging, I will use the variation of resonance phase. So here I presented the so-called slow fast system. To a system, I need to consider the vicinity of a resonance surface in a system phase space, and to rescale independent variables, and to introduce one more variables which characterize the distance to resonance phase. So it's more or less usual procedure, and it describes. It can be found in a book by Arnold Kozlov and Neistat, and in many, it was used by many specialists. So it's usual techniques. Okay, and my aim is to average right parts of equation for slow variables. It's convenient for me to use again the orbital Keplerian elements instead of Nonlinear elements. Actually, this system is a Hamiltonian one, but Hamiltonian structure is a little bit unusual in connection with ordinary textbook on Hamiltonian dynamics. Okay, so my aim to average the last parts, or the right parts of a motion equation for slow variables over the variation of a resonance phase. Okay, and if I put this parameter epsilon, epsilon is a square root of a mass ratio of the Sun and Jupiter. It's a small parameter of the problem. So if I put this parameter, if this parameter is equal to 0, E and omega will be constants. And I will have a 1-degree Hamiltonian system which describe the behavior of resonance phase and conjugate variable. This so-called phase subsystem. This 1-degree of freedom Hamiltonian system is an integrable one, so I can find solution of this system, and then I will use this solution for averaging procedure. Of course, in general case, numerical methods are applied to for averaging. But for application of averaging methods, it's important to know the qualitative properties of solution in this first subsystem. Often enough, mathematical pendulum is considered as some kind of paradigm of resonance behavior. And yes, if we are lucky, the behavior of variables in a first subsystem will be resemble the behavior of variables in a mathematical pendulum. In particular, the phase period of this system will be similar to phase period of mathematical pendulum. But sometimes the situation is more difficult. And why a mathematical pendulum is a good approximation, is a usual approximation for resonance behavior? Because mathematical pendulum correspond to the how to say, we can consider the Fourier expansion of the right part of motion equation, and if our right parts are described by analytical function, the Fourier series will be divergent and coefficient will be decrease in exponential way. So in more situations, the first coefficient in this expansion is the leading one. And for this reason, the pendulum approximation is so effective. But sometimes the first coefficient is absent or small enough, and in that case, the behavioral function will depend on the other harmonics of Fourier series, and we will have more complicated behavior of a resonance phase. In particular, in this case, we see the coexistence of two resonance regimes where the resonance phase oscillates. Okay, so for averaging over the resonance phase, we need to investigate the properties of phase subsystems and to find the region where the pendulum approximation is wrong. On this diagram, this region are drawn in blue. Well, and after such preliminary analysis, I can apply the averaging of variation of resonance phase to find the evolution of slow variables. And what's important? As I said, first subsystem which characterize the behavior of a resonant phase and corresponding conjugate variables is 1 degree. In the case when we consider a limit case epsilon equals 0, we obtain 1 degree of freedom Hamiltonian system which depends on E and omega as parameters. In general case, when epsilon is not 0, we can interpret the behavior of a resonance phase, and we can interpret system which characterize the behavior of a resonant phase and conjugate variables as 1 degree of freedom system which depends on slowly varying parameter E and omega. When we have a 1 degree of system which depends on slowly varying parameters, it means that we have an adiabatic invariance. And this adiabatic invariance will be an integral of this averaged equation for slow variables. In another way, to construct phase portraits of this system, we can compute the adiabatic invariance, and the level lines of this adiabatic invariance will provide us with will allow us to construct phase portraits. And in this way, I constructed a set of phase portraits which characterize the evolution of an object in a retrograde coorbital motion for different initial conditions, for different values of exact and approximate integral of motion, and different an interesting dynamical phenomena which can be discussed in this context is the formation of so-called adiabatic chaos. Because for some initial condition, the motion of the asteroid will demonstrate the transition from resonance to non-resonant behavior. Here the green region corresponds to a region where the resonant phase rotates, so it corresponds to non-resonant motion. And during the evolution, so in a green region we will have a non-resonant motion, outside green region we have a resonant motion, and every time when a transition from resonance to non-resonant motion takes place, there will be a jump, small jump of adiabatic resonance values. This jump has quasi-probabilistic nature, and after the several jumps we have a diffusion of real phase trajectory projection on the phase plane of slow variables. So these trajectories correspond to the phase trajectory of a double average motion equation, and we consider the projection of a real phase trajectory of non-average equation on this plane of slow variables. And every time when a real phase trajectory projects across these borders, there will be a small jumps of adiabatic invariance. In other words, it will jump from one trajectory of average equation to the another, and after the series of these jumps, we will obtain a region of adiabatic chaos in the phase space of the system. Okay, this system characterized also by so-called formation of so-called geometrical chaos, but I will not consider this mechanism of chaotization in my talk. I can mention that it was investigated in details in the papers actually by Neistat and some of his colleagues from Space Research Institute. Here I presented numerically obtained results for one really existing object in a retrograde coorbital motion. And so my conclusion of my talks. So adiabatic approximation can be used for studies of mean motion resonances without any restriction on eccentricities and inclination. It's very important for people who are working on these kind of problems, because classical methods of mean motion resonance studies valid for cases when eccentricities and inclination are small enough. I suppose to consider an implication of these techniques for so-called non-restricted three-body problem. So in the case of restricted three-body problem, we suppose that mass of one of the bodies is equals 0, but in the case of mean motion resonances in exoplanetary system, we are forced to consider the situation when two planets have comparable masses, and for this reason the model with restricted three-body problem cannot be used as a model to study the dynamics. Okay, here I presented some publications, my publication where this approach was applied to different resonance situation in the motion of celestial bodies, and thank you for your attention.
Any questions or remarks? Well, in that case, okay, please.
It's a very interesting question, because this asteroid sorry. The direct numerical integration, retrograde reverse numerical integration demonstrates that the time of this motion, of this asteroid motion in retrograde orbit is comparable with the age of our solar system. And it's very surprising. It was very surprising for specialists in celestial mechanics, and because according to usual concept of a solar system formation, as a consequence of the the consequence of hypothesis that most of planets were formed from the protoplanet cloud. Most of objects, practically all objects in the solar system should rotate in the same direction, at least at the time of a solar system formation. And a hypothesis was proposed that maybe this object was has an interstellar origin and was captured by our solar system long ago. But there are different positions of specialists in celestial mechanics with respect to this hypothesis. There are a lot of doubts that that this object has interstellar origin.
Right, so if there are no other questions, so let's thank the speaker again. So the next speaker is Alexei Rosaev.
First of all, thank you very much to organizer of this conference to give me ability to talk at this conference. My contribution is continued the celestial mechanics topics in conference and the resonance orbit 2. The problem setting is very simple. Planetary n-body problem with star in the center of system, n planets with mass m, g, m, e, and one massless planet, asteroid m. Let the asteroid m orbits in vicinity of main motion resonance. It is well known that integration of the solar system object leads to chaos in a very short time interval. As show last curve, the integration time cannot be more than 60 million years due to Ceres and Vesta orbit chaoticity. In the most recent publication, Radovich showed that the backward integration method restricted by 80 billion years for asteroid fallings. Our numeric integration, preliminary numeric integration of asteroids orbits near 3-to-1 resonance with Jupiter, we have found that instability is in a shorter interval already since 1 million years or few 100,000 years. To study this problem numerically, in this paper, the equation of motions was integrated with the n-body integrator Mercury and by Eberhard integration method. First, I consider the dissipative system, how the dissipation may be present is celestial mechanics in the dynamics of our solar system. It is well known Yarkovsky effect when the thermal force not equal heating of the surface of the small solar system body leads to depends of semi-major axis of Thieme and the drift, so-called Yarkovsky drift in semi-major axis. This drift can be as well positive as well negative, independence of the rotation, direction of rotation of asteroid around its axis. We perform backward integration noted by blue line, and after that we use final values of coordinates and velocity inserted in integrator and repeat this integration to forward since the final epoch which we obtain in backward integration. In result, we can see very good coincidence forward and backward integration, but only in case when the resonance are absent. Just if we encounter with the main motion resonance, we see that these trajectories differ. Our first integration, backward integration, show the more resonance perturbation when the integration forward, since the last point is more fast jump in the resonance. And this picture show is more detail. It is more harder, harder picture in our integration. Backward integration, we have increasing the semi-major axis. In this case, we study resonance with Jupiter, and in this direction we approach to the Jupiter backward integration. Then we start forward integration. We go away to orbit Jupiter, and in this case we see a jump and a fast moving of the resonance zone. Instead, in the backward integration, we have a long time capture into the near resonance area. How can it be exploited? In these tables, we more in more detail gives result our experiment. In different initial eccentricity, we have the same effect when the difference at the epoch 0 is present and reach large value, about 200 of astronomical unit. It is very large value, and in the last two columns we give a time of capture in resonance in the backward trajectory and in the forward trajectory, respectively. In this case, we can see that in all cases, the time of capture in backward motion is longer than in forward motion. But how can it be exploited? First explanation, of course, is very simple. Is due to round-off error, because we cannot give the initial conditions with infinite occurrence. But instead exists the second explanation, explanation is given by in the book Murray and Dermot. According to the Murray and Dermot theory, we have they consider the Hamiltonian second fundamental model of resonance, and with the value of constant written here, and the main parameter is delta. Delta is a measure of distance between exact resonance. When delta increase, divergent orbit, the capture in resonance is impossible. And if delta decreasing, when the orbit asteroid and planet which resonant with asteroid converged, capture is possible with finite probability, independence of eccentricity value. If such a model is true, I obtain the numeric result not in contradiction of this model, but I cannot say that I confirm this model, but this model is not in contradiction with our result. The next, we try to consider the conservative system. Can the resonant capture and jump from one side of resonance to another side be possible in pure gravity system without any dissipation? To consider this question, I study the Datura asteroid family, very young asteroid family, and a few members of this family. First of all, in the last line, asteroid number H9039, and integrate a few clones in the vicinity of initial orbits in so-called 3 sigma interval, in interval of orbit uncertainties. Yes, how you can see, the jump in gravity, full gravity system is possible, and you can see that we have two branches. First, jump from one side of resonance and to another side of the resonance is very exactly confirmed for any clones, but second jump is poorly determined by initial conditions and subdivided to two branches. When in the first jumps is absent and the second jump is present. Important our result that jumps in Datura family, an asteroid of Datura family in orbit, jump in the semi-major axis, take place in the same epoch, about 60,000 years ago, and 310,000 years ago, for all members of this family. It illustration for the previous my sentence, when the number of clones have the second jump approximately equal the number of clones which have no jump. This is a distribution of semi-major axis at epoch 450,000 years is epoch of supposed age of the Datura family. It is easy to see that close to resonance, semi-major axis are avoided and has a very low probability. as a small conclusion about this picture, the choice between two branches can be made only with the help of additional information, like the Yarkovsky effect measurement or any other additional non-dynamical information. Then we can find the reason why the jump take place. In the more detailed consideration, each main motion resonance consists of the multiplet of the lines in semi-major axis with finite width, as is shown in these equations. The position of the lines of multiplets depends on Perigelian argument position and by another word depends on the right of the position of orbit and the right of the position of orbital plane of asteroid, and the same about the orbit of the perturbing planet. Well-known Lagrange equations used for the determination the rate of orbital plane. If we restrict the lowest order of perturbation function, we have the rotation of the orbital plane, a constant rotation of orbital plane. But it is insufficient in this case, and to obtain more exact value of this rate of the precession of the orbital plane, we need to take into account the higher orders of perturbation function. We use the perturbation function expansion by Murray and Dermot, is expert Murray and Dermot, and obtain the following final expression. This is the expression with two constant. Of course, for C4 is larger than C5, and as a result, we obtain the expression for the velocity or rate of the pulsation. How you can see, in the case of the small value of inclination of asteroid orbit, we can change the sign of the orbital motion, orbital plane motion. Yes, if we apply this expression to Mars orbit, we can see that bold line is a node of Mars, and the thin line is a inclination of Mars. When the orbit of Mars have very small inclination, smaller than 1 degree, we have the inversion in the orbit plane precession. Evidently, according to the previous equations for resonant multiplet, we have changed the weights and the position of terms in the resonant multiplet. Like this. This is the case of the normal orbital precession, is the case inverted orbital precession. After evidently this change of the weights and position of the multiplet can lead to collision of the orbit of asteroid moving in the vicinity of the resonance with the resonance and leads to the jump and temporary capture of the orbit into the resonance. Additionally, we can fit the solution when the exact equality of the coefficient is the formula. We have the oscillation of node instead the node precession. In this case, the orbit orbital plane not rotate and only vibrate around the fixed position. In the numeric integration, such kind of the motion was found for the case of the 3-to-1 resonance with Jupiter as initial conditions here. In the data, if we consider the non-overaged equation is the most detailed step, we can see that the change, the jump from one position of the semi-Majorakis, averaged value of semi-Majorakis to the another value semi-Majorakis, jump take place through a temporary capture into resonance. There are two cycles of with large amplitude, and after that we obtain the averaged different value of semi-Majorakis. It confirms the case that temporary capture can take place in the pure gravity system, not only in the system with dissipation. So we can give the conclusions. Local conclusions is evident. The backward integration of orbits collided with resonance, very unstable, and can give false result and required a very careful interpretation. And the global conclusions may be following. If the model of Murray and Dermot or any other model with asymmetry of resonance, area in vicinity of resonance is true, the gravity system with resonance can be non-symmetry relative to the signal of time inversion. Thank you very much.
Any questions or comments? Yeah, sorry. I wasn't sure who was first.
Spin state of asteroid. If you apply backward integration for 1 million of years, did you estimate the changes in asteroid rotation state? Do you take it into account?
Так, sorry.
Изменение вращения астероида.
No, we not know about any parameters of asteroid, but of Yarkovsky effect we use only only in the form. Yes. Only the form coefficient A2, and we give a very large value of A2 in order by searching with minds. It is large value. Really, it is by order smaller.
Okay, thank you.
Thank you. And it's one more question.
Maybe I'll skip my question to coffee break.
Okay, question is postponed to coffee break. So let's thank the speaker again. Thank you. So the next talk will be online. So the next speaker is Margarita Preobrazhenskaya, and I need to share the Rita, just give 1 second. I'm trying to figure out how
Okay, okay.
Вы случайно не знаете, как мне дать ей разрешение продемонстрировать ее экран? Ага. Участники, ага. Не, да, то я вижу, просто тут, к сожалению, нет. Ага. So Rita, I'm going to make you administrator, but then you need to give me administration rights back. So you are now administrator, so you can do whatever you want. You can share your screen.
Okay. So let me start. Is it visible?
Yeah, everything.
My screen? Are you visible? View my screen? Yes.
Yeah, construction of cycles. We can see it. Yeah.
Dear colleagues, I'm going to talk about the model of ring of relay oscillator. These oscillator are neuron type. And this work is common with Sergei Glizin. I'm going to start with the simplest phenomenological model of neuron with delay. And here U is the membrane potential of neuron. Parameter lambda characterizes the rate of the electrical processes. Here function F characterizes conductivity of ion channels. This model is more simple than analogical model invoked Kolesov, Millionshchikov, and Rosaev. It was article 9010. They prove that such equation, as you can see, have relaxation stable periodic solution U0, which have high burst per period. You can see the picture. And the main object of my work is the ring of M unidirectly synaptically coupled neurons. Here, every neuron is modeled by equation which were at the previous slide. The function F is the same. Membrane potential of every neuron is denoted by UG. UG is more than 0, and the important feature is the second term in every equation with function G. This term model synaptical coupling. Here we use idea of fast threshold modulation for construction this model. And here logarithm in second term have parameter U star, and this is threshold parameter. And when UG cross U star, the second term change its sign. So we have in this moment we have coupling, and one neuron acts to other neuron. I'm going to concentrate on several effects. The first is bursting behavior of neurons. This is a phenomenon of alternation of several consecutive intensive spikes with relatively smooth region of membrane potentials. You can see the picture. We have several bursts, and then small enough value, and then again several bursts. This is for periodic solution. The second effect is multi-stability. If system have an arbitrarily fixed number of stable periodic modes, we said that the system has multi-stability. And if we have also a special mechanism of solution accumulation, then we say that we have bursting phenomenon. I'm sorry, buffering phenomenon. Buffer phenomenon. And I want to tell you about case of M equal 2 when we have only 2 neurons. And for this case, we proved the theorem, and we proved that the system has K stable solutions which have the following feature. We fix natural K, and for this K, components of function U, I mean U1 and U2, have one and the same summarizing bursts. In first case, we have 3 plus 1. In the second, 2 plus 2. And in the third case, 1 plus 3. This is in the case K equal 3, for example. But it is true for every K. We can use arbitrary K. It was our common work with Sergei Glizin, and the first about K coexisting stable solutions means multi-stability, and the second feature is bursting for every component, and we can say that this system have buffer phenomenon because we can show the mechanism of accumulation, of solution accumulations. And now I want to tell about generalization, that idea. And now I again want to talk about the system of M neurons. And I fix M natural numbers, and I want to construct solutions such that every component have bursting effect, and every component have fixed number of bursts. For U1, this is K1. For U2, this is K2, and etc. So every U have exactly K high bursts, and it has long enough interval with small value after these bursts. I want to tell about sketch of this theorem, and the typical way to prove such theorems is change variables, and I make exponential substitution. New variable is x instead of u. We also have a function r and h instead of f and g with exponential argument. And note that when we change variables, bursts for function u becomes positive intervals for function x, because x is in exponent. And when you have small value, function x should be negative. So we are interesting now such solution with positive segments and long negative segment. Let me note that function h change its value when x argument x change its value and cross by 0. Function h big becomes 0 if argument is negative. So it is necessary to consider the additional task when the second term is 0. And I can formulate the lemma about this task. I remind here what is function r. It is relay function, and I give initial function psi. It is continuous function on the segment which have length h. This is a biggest delay. This function is 0 at point 0 and have negative value at initial segment. So it is possible to prove that the solution of this task have a periodic solution, which you can see at the picture with these linear functions. Then I choose initial set for my big task for system by variable x. And I suppose that every component have the similest view as at previous case. And here I fix m numbers. First of them is 0 and other more than 0. And I suppose that for every component, values at initial segment are negative, and at point 0, value have fixed meaning. It is minus d sub g. And the big initial set is S, which is this product, S1 and etc. Sm. And I prove the theorem about system for logarithm scale variables x. And I prove that I can construct such solution with Cauchy positive segments for every components, and every component have long enough negative interval. After that, I want to tell about this theorem, about proving this theorem. I construct Poincare map. For this goal, I construct by hand solution for the long enough segment, and then I construct Poincare map. This formula 2. I defined it by solution. Here, function x is a solution which I construct for some segment, and I used value t1. This is a positive root of equation 1. I suppose that the root with number 2k1 exists, and denoted by t1. So I have the map which by function phi1 functions phi1 and etc. phi-m, which are brown at my picture, construct the picture. Construct the also brown function, which is denoted by pi phi. It's on the right side of my picture, and we see that we can see that this map has fixed point because a negative function go to negative function, and important is the separated map for vector d, and we should show that this map has fixed point. And we can construct it. And also this map says about stability of solution. And we can analyze this map for give answer about stability for this system, for this solution. So it was about sketch of the theorem, and now conclusion of this work. We consider a ring of M unidirectionally synaptically coupled neurons. For this ring, we present a new approach to model it because we refuse from continuous function in right paths. We use relay functions, but we have the same effects as in continuous model, but proof of these results is more simple for this case because model is not so difficult. Also, I want to say that delay in a coupling is important because it was important for construction solutions. For case M equal 2, we have bursting and multi-stability phenomenon, exactly buffering phenomenon. We prove this theorem. And for common case, when M is arbitrary, we make generalization of idea which used in case of M equal 2. This is all. Thank you for your attention.
Thank you very much, Rita. So, are there any questions or comments? Okay, probably not. So,
I'm sorry, I have a question.
Yeah, please, Dima.
Rita, could you say if there's some approach of the same technique to more complicated neural networks, the neural networks which are used in informatics, so with this with the more complicated graph structure?
No, you mean not ring, but more complicated? I think it is possible in some form. Maybe yes.
Thank you.
Not for all forms of graph.
Thank you.
So,
thank you for the question.
Any other questions or comments? Okay, in which case we will have a break for 30 minutes and we come back in half an hour, so at 4:30, but Moscow time. So, Rita, thanks again very much. But you need to return my administration rights. So you just need to find me in the list.